So let's look at an example how we're going to use this transfer function to find out the sinusoidal steady state response. And in this case, we have the circuit, very simple RC circuit. We have the resistance, this is 10 kilo ohm. And we have the capacitance, that's 0.1 microfarad. This is the parameter we're going to use when we do the experiment. So in this case, we have the three different types of input. We're trying to find the output, the steady state response output. So since we are using the transfer function, we'll first find out the transfer function. Okay, the transfer function, let's see, this is simple one, so this is TVS, that's equal V2S over V1S. This straightforward voltage division, so that's 1 over CS over R plus 1 over CS, and therefore I have 1 over, I have S. So if we multiply CS on both sides, right? So we have 1 over RCS plus 1, RCS plus 1, or we can, if we want the coefficient in front of S as 1, we will divide by RC on both numerators. So 1 over RC plus 1 S plus 1 over RC. And RC is equal to 10K times 0.1 micro. So we got equal to 0.001, 10 to the power negative 3, right? 10 times 0.1, that's 1. So therefore we got 1. In this case, actually, it's the unit RC is time constant. That's 1 millisecond, right? So that's 0.001 second. And therefore the TV is equal to 1,000 over S plus 1,000. Okay. So with that, we can find the three different steady state response. Let's see that for the first one, VT is equal 2 times 100T. So in this case, omega. So we're going to replace. So in this case, Tj omega is equal T J 100, and that's equal 1,000 over 100J plus 1,000, and so this is the transfer function, right? So in this case, we write this in the polar form, right? In the polar form, it should be something like. So there are a couple of ways of doing the polar form. The polar form, you can convert the numerator to the polar form. So in this case, the numerator here, the denominator here, 100 square plus here the 1,000 square. This is what you would do, calculate by hand, and then the angle is going to be arctangent 1,000 divided by 100, which is the arctangent 10, and so the numerator is 1,000. So you can calculate these. And the calculation, I'm not going to calculate by hand. I calculated by the Python code. The Python code is TG100. The magnitude in this case is 0.995, right? So that's 0.995. The angle here, this angle arctangent 10 is 5.7 degrees, and if we invert, then you get a negative 5.7 degrees, and so therefore the amplitude of the output V2, the steady state, we just need to use 2, the original amplitude times the magnitude of the Tj omega, right? So therefore the V2, we're going to write it in this way. So that's going to be 2 times 0.995. That's the amplitude for the output response. And then times, we don't need to change the sine or cosine. We don't have to work with the cosine in this case. So we just need to add the phase angle. The original, that's 0, right? 0 plus the negative 5.7 degrees. So that's quite straightforward, right? So in this case, we got a 1.99 times sine 100t plus minus 5.7 degrees, and this many volts. So this is for the first one. And for the second one here, they're similar. So in this case, Tj omega is going to be equal to T 1000. So the second one here, we have the 1000t, right? The angular frequency omega is 1000 radian per second. Make sure you distinguish between the hertz and radian per second, right? The radian per second, if we convert to hertz, this should be 1000 divided by 2 pi, right? So in that case, divided by 6.2 is something like 150, close to 150 hertz. So this is 1000. And so in this case, we got a 1000 over 1000 j. We replace s by 1000j plus 1000. And so therefore, in this case, we can do the similar calculation. And we actually have 1000 over 1000 square. Actually, this is square root 2 1000. If you're familiar with this polar rectangular transformation. And so in this case, the arctangent, in this case, arctangent 1000 over 1000 arctangent 1, that's the 45 degrees, right? So therefore, we got 1000, we got a square root 2, so we get a 1 over square root 2, the phase angle 45 degrees, 45. And so we got a half square, or 1 over square root 2 times negative 45 degrees. So this is the polar form of the Tj omega function. And then therefore we can get the output. So in this case, what the output, the input. So you input now the cosine function. Make sure we use the cosine. So we got a 2 times. So the V2t is going to be equal to 2 times and square root 2 over 2 times cosine omega t, which is 1000t. So 1000t in this case minus 45 degrees. So in this case is 1.1414 times the cosine 1000t minus 45 degrees. And we realize that we have originally for at 100 radian per second, we got 1.99, which is very close to the origin, to the input magnitude. Right now we got a 1.414, and let's see at the 10,000 radian per second. So at 3, we have a t j omega is equal. So that's a t j 10,000. In this case, I have 1,000 over 10 to the power 4th j plus 1,000. So you can do the calculation. Similar calculation, we got 0.0995 times the phase angle is negative 84.3 degrees. So that's the for the TJ3, and in this case the V2, and let's pay attention to what the V1 is for this case. V1 is 2, and now we have this phase angle of 30 degrees, and we use the sine function, so we're going to use sine function in the output also, and we got a 2 times 0.0995 and times sine a 10 to the power 10k radian per second t minus 30 degrees, plus 30 degrees, minus 84.3 degrees. So the result here, we got a 0.199 times sine 10 to the power 4th t minus 45 degrees, 54 degrees, 54.3 degrees. So this is for this example here. And we can see here, at a higher frequency, the magnitude, the amplitude of the output really low now, right? It's 0.99199, which is 10 times lower, right? 10 times lower than the original we have for this case. So we have all these three cases solved, and this is how we would use the transfer function to find out the steady state sinusoidal responses. Okay, and I'm gonna see you for in a moment for the frequency response.